So before I launch into the example, I don't think it's unreasonable to consider that if you were at the very center of the earth, if we could just get you there, that you would experience no force due to gravity at the center of the earth. Is that a believable statement? That you have equal amounts of earth all around you? So the force of attraction between you and every other part of the earth would cancel out. Is that reasonable? We're just talking about symmetry here. So consider that there is a piece of mass that's acting on you, pulling you this way, but there is a symmetrical piece of mass over here that pulls you this way. And due to the spherical nature of the earth, we could say that that would happen everywhere. Agreed? All right. Now, let's get our hole back in the middle of the earth. This one's going to be harder for you to believe. And I could prove it if you had more calculus. So for the few of you who have enough calculus, I could prove it, but I'm not going to. It's not worth the energy. But I want you to consider that even if there was a large cavity in the center of the earth, we would still have the same problem, right? That if we were at the center of that cavity, we would experience no force due to gravity from the earth. That all okay? Any problem with that? Now, look, this is a thought experiment, so just keep in mind that if the moon were out here, you'd be attracted to the moon. Okay, but we're going to ignore the influence of the moon, the sun, the other planets. We're just talking about the earth, okay? This part's harder, and you don't have to take my word on it. It can be proved using calculus, but it's not easy to do. But the statement I just made about your experience of net force is the same even if you're not at the center. That everywhere inside this cavity, you'd experience a net force of 0 due to the gravity of the earth. You don't have to believe me. It can be shown using polar coordinates and a careful calculation using calculus, where you have to add up the contribution to the force from every piece. Because consider this piece right here. This piece is closer to me. This piece might be further from me. But if we draw a line, kind of through the middle, there's less mass on this total side, but it's closer to me. There's more mass on this side, but it's further away from me. It can be shown mathematically, because this is a sphere, that those would be equal contributions to the force, and you would still experience a net force of 0. I'm not going to show that to you, because I really don't think it would be worth the venture. But can you walk with me with that idea being okay? It's plausible. There's symmetry there. So can you buy along with the symmetry? Now here's why I want to have this conversation. And you needed to have this little bit of backstory first. If you were to carefully drill a hole through the center of the earth, no, we can't do this. No matter what the movies say, no. So if you've ever subjected yourself to the movie The Core, no, we're not doing it. We're not drilling a hole to the core of the earth. But let's say that we could. If you dropped something in, say, here, is it reasonable to believe that it would gain speed as it fell through this hole? Until it makes it, say, to the center, where we know for that moment it would experience a net force of 0. And then as it makes its way to here, it should just pop up on the other side. And if the person on the other side isn't fast enough to catch it, doesn't it go back through the hole and the same thing occurs? Does this constitute an oscillator? Can the symmetry of the situation suggest that this might be harmonic? and that it would probably take the same amount of time to go back as it took to get there. So the real question would be, is it a simple harmonic oscillator? I think we could maybe prove it and see. Now, I want to use this as an example, maybe looking at the net force on an object when it's, say, here. Is that okay? This is displaced a distance x from the center. The center is the equilibrium position. So I'm displacing it a distance x and releasing it. If you want, we could displace it from here, but I'm interested in talking about what the forces are of the object here in the middle, because I think that's where it's interesting. Does that make sense? We could talk about it here, but I don't think the force is constant. Based on the argument I made just a little bit ago, when we are, say, at that location x away from the center, the entire Earth is not contributing to the force of gravity on us. Remember, if this were just a shell inside there, right? If this was this outside portion here, it's not contributing at all to the force of gravity on us. We said that if you're inside this cavity, that portion wouldn't apply a force of gravity on you, because the net force from that shell portion would be 0. So the only part that's contributing to the force of gravity is the part that's inside this circle. Does that make sense? Because the outer shell part isn't pulling on you. So I need to figure out what the force of gravity is on me when I am a distance x away from the center. It's not as hard as it seems. What I really need to do is remind myself that this portion of the Earth right here that's inside, it has a radius of x, right? So I want to find the mass of that sphere. I'm going to use a subscript here, and I'm going to say the mass of the sphere that we've defined by x. Now, what I'm going to do is I'm going to take the whole mass of the Earth and compare it to the volume of the Earth, and set that equal to the mass of the sphere and compare it to the volume of the sphere. This should give me a way of writing what the mass of that sphere is. And then I'm going to remember that currently the force of gravity on me comes from the mass of the sphere, g, and how far away I am separated from the center of the sphere squared. Right? Isn't this the force of gravity equation? This should equal mass of me times A. All good so far? I am considering how the system oscillates. I'm going to try looking at the forces. If the system was displaced, I'm going to apply Newton's second law. And, I should probably consider the direction of this force. Can we agree that if x is positive, this force is negative? Right, because it's back towards the center? All right. All right, let's go ahead and see if we can come up with an expression for the mass of the Earth. And I want this mass of the Earth to be in terms of x. Because as I fall towards the center, there's less and less Earth acting on me. When I make it to the center, there's no Earth acting on me. I think this expression will help. I don't really need the mass of the Earth for this, but the volume of the Earth will be 4/3 pi radius of the Earth cubed. right? That's the volume of a sphere. And now we have the mass of the sphere I'm carving out, the green mass, which would be 4/3 pi x cubed. All I'm saying is that the density of the Earth is the same everywhere. It's not, by the way. That's taking a big liberty. The density of the Earth varies as you get closer and closer to the center, the crust being less dense than the chewy center. But we're just playing a game, right? We can't actually drill a hole through the center of the Earth, so it doesn't really matter, right? Just for funsies. I can solve this for the mass of my sphere, but can we agree before I even start that the 4/3 pi cancels out on both sides? Leaving me with mass of the Earth times this ratio, x cubed to radius of the Earth cubed. I like having this ratio here because the units of this, just one, there's no units there, right? It's meters cubed divided by meters cubed. Telling you that the mass of the sphere is equivalent to whatever units the mass of the Earth is in. I like that. Also, I think we just go ahead and substitute it over on the other side. Now, I'm going to write it all in there because you guys tend to just write down anything, but we'll have the mass of me, the mass of the sphere, which is mass of Earth, x cubed, radius of the Earth cubed, g, all over x squared, times mass of me times a. That's messy. But I think we can simplify. First, let's get rid of the mass of me. I don't need that in there. And I see x squared and x cubed. So I'm going to get rid of the cubed. And I'm going to combine like terms. So when I combine like terms, I'll have mass of the Earth times g over radius of the Earth cubed times x. You guys see all that okay? Well, this looks like A equals minus a whole bunch of stuff in here times a displacement. Is that what you see? That's what I see. I think we can figure out how long it would take for you to travel down this path. All we have to do now is recognize that this is omega squared. And because that's omega squared, you can figure out the period of oscillation. Period of oscillation is just 2 pi divided by omega. So 2 pi divided by omega, that'll be 2 pi times the square root of the radius of the Earth cubed divided by mass of the Earth times g. That's how long it would take. So if we were successful and could drill a hole down the center of the Earth, this would tell us how long it would take before we came back. Do me a favor. Work that out. Just a ballpark estimate. Radius of the Earth, mass of the Earth. See, mass of the Earth is 6 times 10 to the 24th kilograms. Radius of the Earth doesn't stick for whatever reason. What G is, right? Now, I'm not interested in all of you getting different values, so if you could get it right the first time, that would be great. And make sure you convert it to something appropriate. So something that makes reasonable sense. Seconds is the default. So let's see if we can move it to something that makes more sense. I get 84.7 minutes. Now, that's how long it takes to go from here to there and back. So if I divided it by 2, I get 42 minutes. So if you just wanted to go someplace on the other side of the planet, it takes 42 minutes to get there. Here's what's interesting. You guys, it's not hard to do the math. You just have to add a little trig. If you add a little trig and redo this, you can actually drill that hole between any 2 points on the planet. Any 2 points on the planet. Now, the force is still towards the center here, so you'd only be dealing with a portion of the force, down your hole. Do you see that because of the angle? But if you do the trig and just add the trig to this, you find that the force is reduced proportionally. So the period is still 84 minutes, no matter which 2 places on the planet you connect. Which means if you could drill a hole from here to, say, San Diego, it would take you 42 minutes to get there one way. You'd have to find a way to reduce the friction and stuff because, truthfully, you'd be going very fast in some parts of this. So evacuate out the air, use a maglev train, all that kind of stuff. But yeah, if you connect any 2 points on the planet, even if you could just add enough energy to overcome the friction the whole time, imagine, it would just be a little bit longer than 42 minutes, no matter where you wanted to go on the planet. But we're not drilling holes like this through the planet. I don't care what you think, we're not doing it. The deepest holes that we get are never that deep, and we'd have to be several hundred miles in some places. So no, we're not doing this, but it's just an interesting thought experiment. But while we're on this topic of this thought experiment, and because a few minutes ago, perhaps look here. Are they not the same? How about this? Vmax is equal to omega times x max, right? For all oscillators, this is true. Well, omega, we have it there, right? Omega is MEG over RE cubed. That's omega. So Vmax has to be MEG over RE cubed times RE. That's what X max was, wasn't it? So do you see why I'm doing that? I mean, I really want you guys are so terribly smart and can do this without my assistance, I am sure. Do me a favor, will you? What if I wanted to ask you to do something that you used to do first semester? I've been showing and being concerned about your capabilities. So here's what I want. Imagine that we're just going to put something in orbit right near the edge of the Earth. Can you figure out how long it would take to go around the Earth if you were in orbit right towards the edge? I don't want the number, the expression. You did this first semester, so if you don't remember, just look at your notes from first semester. They're there. I'll put one hint and only one hint on the board. And this is because, I know your guys' memories are not ideal any longer. It's like you're all 80-something years old. Just reminding you about something. So you should be able to do this. I'll give you, and we found this quite literally last week when we talked, or the last time we talked about orbits, which was 2 weeks ago. This should not be hard for you to figure out the velocity. I will pick on one of you in just a minute. Good. Net force equals MAC for an object that's in orbit. So mass of the Earth, mass of the object, G over radius of the Earth squared equals mass of the object times, I don't know, how about V squared over radius of the Earth? I have no reason to slow down here, right? Because we've done this at least a dozen times. So cancel, 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 cancel. We find that V is equal to the root of MEG over RE. And then I just said, please find the period. All right, well, that's not too much. I gave you the expression for period. You're just going to plug it in there. But this is 2 pi r for the Earth divided by the root of all that. But instead of doing it that way, I'm going to save myself a little time and just invert. So 2 pi RE times the root of RE over MEG. And because I want you to see something, I'm going to put the R inside the radical, which gives us a period equals 2 pi times the root of RE cubed over MEG. Right? Right, you see why I'm doing this in the first place? I mean, for those who can't remember, isn't that the same thing we found over here? Circular motion and periodic motion are very similar. Very similar. In fact, I have 2 springs that are connected together. There's 2 ways to do this problem. This is the harder of the 2. So the other way to consider this problem, I don't really think I should have to do with you. I think you guys should be able to figure it out on your own. It's if you have the same 2 springs, but are capable of fastening on either side of the mass. So say something like this. So K1, K2, here in the middle. I think this one's pretty easy. I think if I asked you to figure out what the period of oscillation was here, I don't think you'd have much trouble. I'm concerned because I'm just looking at the looks on your faces, but I don't think you'd have much trouble. In fact, maybe try just for a second to see what you get. You know, maybe start with considering what would be the forces if you displaced it a small amount to the side. Notice that's kind of where we started all of these. Like, do you think this would oscillate? Okay, do you think it would oscillate in a regular way? If you do, then maybe consider what the net force on it would be. Now, it should have been a whole bunch. If we're looking at the top one, how many forces act on the box? I'm sorry, we look at the one on the right. How many forces act on the box if it's displaced? 2, right? This spring pulls to the left on the box if it's displaced to the right. And this spring pushes to the left on the box if it's displaced to the right. So that one's pretty easy. Net force has got to equal minus K1x minus K2x. Is there any reason to believe otherwise? 2 forces, both pushing in the same direction. The displacement of both springs is the same. So I can just write this as MA equals minus K1 plus K2 times X. I don't know what you guys are doing. I don't know why. I mean, this is right here. It's these things. So A equals minus K1 plus K2 over M times X. This is omega squared. How many forces are acting on the box in the situation on the left? Just one. There's only one spring touching it. Right? Do you think the 2 springs are working together? Something's got to be happening. Here's the problem with the situation on the left. X represents how far the block was displaced. That does not represent how far each spring stretched. You see, spring 1 probably stretched a distance x1, and spring 2 probably stretched a distance x2. I would bet that x1 plus x2 equals x. Now here's the part you won't probably see coming. This point right here. You see, the net force on that point has to be 0, with one spring pulling to the left with the same amount of force that the other spring pulls to the right. Because if they were unbalanced, then it would accelerate one way or the other. But that point is instantaneously at rest, because this is all like one long rope and has to have the same tension throughout. So at this point right here, the net force to the left from spring 1 has to be equal to the force from spring 2 to the right. So K1, X1 2. I'm giving you 2 hints, because you still, if you want to get the period, A has to equal a minus sign times something times the displacement of the box, x. This is a hint, because this is one of your homework questions. Again, you're trying to find the period. By extension, trying to find omega. This one's hard. This one's easy.